Dr. Y. Sarada, Professor, Department of Mathematics, Anna University. Her area of specialization is applied probability and stochastic modeling. She has about 25 research publications in national and international journals. She has guided students for research projects. She has delivered lectures in her area of specialization in many institutions.
Welcome to the UGC lecture series on queuing and reliability. In the last episode, we saw the exponential random variable and the postulates of the Poisson process. Presently, we will focus on the derivation of the Poisson process using the postulates of the Poisson process. And I wish to mention about the importance of the exponential random variable at this stage. Namely, an exponential random variable is a random variable which represents maybe the time between two consecutive events or the successive events. It is only one type of event we will be looking on the time axis. So, the time between any two consecutive events that comprises the exponential random variable. We will see the link between the exponential random variable and the Poisson process in today's lecture. We saw the postulates of the Poisson process earlier. Now, the definition of the Poisson process is given by the following. The counting process NT, t greater than or equal to 0, is said to be a Poisson process having rate lambda which is positive if three conditions are to be satisfied. First one, n of 0 is 0. About this I already spoke to you in the last lecture, namely it is a counting process. So, to start with, initially there is no event in the system. So, n of 0 is 0, the count is 0 at time t equal to 0. Next condition is process has independent increments. This we saw that events happening in non-overlapping intervals are independent of each other. The third one speaks about the stationarity, that is the number of events in an interval of length t is Poisson distributed with mean lambda t. For all s t greater than or equal to 0, putting it mathematically, probability of n of t plus s minus n of s equal to n is equal to e power minus lambda t power n by n factorial, and n can be taking the value starting from 0, 1, 2 and so on. Here if you see that earlier I was telling you that probability of nt equal to n is equal to e power minus lambda t power n by n factorial. The notation we saw was pnt. This is also equivalent to the same thing, except that today in this definition on the left hand side I had given you probability of n of t plus s minus n of s equal to n. So, you have to observe this, n of s denotes the number of events in the interval 0 to s, while n of t plus s denotes the number of events in an interval of length t plus s, or the time interval is 0 to s plus t. So, when you subtract the number of events happening in 0 to s from the number of events happening in the length of the interval s plus t, the length is nothing but t. So, ultimately what we are asking is probability that n of t is equal to n, both are equivalent. So, this is the definition of the Poisson process, and the Poisson process is one of the most important integral valid process which serves as a mathematical model for a wide range of empirical phenomena with remarkable accuracy. The postulates of Poisson process, I have it again just as a recap. Independence postulate, the counting process nt is independent of the number of occurrences in an interval of length t. Homogeneity in time depends, the distribution depends only on the length of the interval and is independent of where this interval is situated. And the regularity speaks about an infinitesimal interval of length h, where the probability of exactly one occurrence is, and that of is lambda into h, and that of more than one occurrences of order O of h. We will presently see how these probabilities can be written based on the postulates and the definition that was given earlier. So, P1 of h is lambda h plus O of h. P1 of h speaks about the probability of the occurrence of one event in an interval of length h. So, P1 of h is given by lambda h plus O of h, and the second expression out here is sigma k equal to 2 to infinity p k of h, which is equal to O of h. So, this is the other postulate, namely regular postulate, where we say that probability of more than one occurrence in an interval of length h where h is very small, the probability is written as O of h. And similarly, we have to find what is probability of no event in an interval of length h, namely p naught of h. So, to find this, we make use of the fact that p k of h, sum over probabilities over k, is equal to 1. The total probability axiom is being used here. So, using that, we have what is P1 h, which is lambda h, and P2 of h, P3 of h, all those are O of h. So, how many ever times you add O of h or subtract O of h, the resultant will be written as O of h. So, we have in this fashion, plugging in all these expressions for P1 of h, P2 of h, and so on in this summation, we have P naught of h is equal to 1 minus lambda h plus O of h. Now, regularity says that postulate limit h tending to 0 of O of h by h is equal to 0. We will be making use of this regularity fact in the derivation. Now, we will see the derivation of the Poisson process using the postulates. The theorem is, under postulates 1, 2 and 3, the counting process n of t greater than or equal to 0 follows a Poisson distribution with mean lambda t. That is, P n of t equal to probability of n t equal to n is equal to e power minus lambda t power n by n factorial, n equal to 0, 1, 2, 3, etc. Now, we will see the derivation P n of t plus h, that is, we are interested in probability that in an interval of length t plus h, the number of events that are happening are n. So, P n of t plus h is written as, now we split the entire interval of length t plus h, that is 0 to t plus h, as 0 to t and t to t plus h. Why do we do so? The postulates, in particularly the regularity postulates, allows us to discuss the probability of one event happening in an interval of length h, two events happening in an interval of length h, and so on. So, we have the data about the probabilities of occurrences in an interval of length h units of time. So, we are dividing the entire interval 0 to t plus h as 0 to t and t to t plus h. Now, we are looking into the number of events happening in 0 to t and t to t plus h. But how about these intervals 0 to t and t to t plus h? They are non-overlapping intervals. So, here in order to write the probabilities of the events happening in non-overlapping intervals, namely 0 to t is not overlapping with t to t plus h. So, we write those probabilities as product of individual probabilities. That is why we are able to divide the interval 0 to t plus h as 0 to t and t to t plus h. So, now we will focus on this P n of t plus h, which is given by P n of t. P n of t is the probability that n occurrences have happened in the interval 0 to t, and into probability of one occurrence or no occurrences. So, we have here when by time t itself n events have already happened, then in the interval of length t to t plus h, there should not be any event. So, what is the probability of that event? probability of no event happening in an interval of length h is 1 minus lambda h plus O of h. So, which is P naught of h. So, we write here Pn of t into 1 minus lambda h plus O of h. Now, this is one event, namely n occurrences have already happened by time t, and in t to t plus h there is no event at all, which means that in an interval of 0 to t plus h totally n events have happened, and that is what you want on the left hand side. But hold on, we have few other possible cases here. So, the next one focuses on in an interval of length t p n minus 1 of t. So, n minus 1 events have happened by time t. The probability of that is denoted by p n minus 1 of t. Now, what should happen in the interval of length h units of time? In t to t plus h only one event can happen, because only then the total count goes to n by time t plus h. So, we have the second expression out here, namely p n minus 1 of t into p 1 of h. So, that p 1 of h we already saw is written as lambda h plus O of h. So, this is the second possible case in this type of events. Now, but then it is possible that there could be by time t n minus 2 events, and 2 events can happen in an interval of length h units of time, so that the count by time t plus h remains n. And also there can be another case, namely by time t n minus 3 events can happen, and in the length h units of time 3 more events can happen, and so on. So, all these are mutually exclusive cases. So, out of all these possibilities only one can happen, but we know that if 2 events A and B are mutually exclusive, then P of A union B is written as P of A plus P of B minus P of A intersection B. In particular, if A and B are mutually exclusive, then P of A union B is written as P of A plus P of B. Right. Here all the cases that we have seen till now, namely by time t n events happening, by time t n minus 1 events happening, by time t n minus 2, and so on, all these possibilities are mutually exclusive. So, we do write all these probabilities as sum. So, that is why we have this expression here, namely Pn of t plus h is Pn of t into 1 minus lambda h plus O of h plus Pn minus 1 of t into lambda h plus O of h plus sigma k equal to 2 to n Pn minus k of t into O of h n equal to 1 to 3, and so on. Now, we use the regularity aspect of this Poisson process, and what we do is we take this p and t into 1 in the first expression to the left hand side, and then divide the both sides by h and take the limit as h going to 0 on both sides. So, this gives us the following expression, namely limit h tending to 0 Pn of t plus h minus Pn t by h is equal to minus lambda h plus O of h into Pn t divided by h plus Pn minus 1 of t into lambda h plus O of h by h plus sigma k equal to 2 to n Pn minus k of t into O of h by h. Anyway, n takes the values 1, 2, and so on. This gives us dPnt by dt. If you see, the expression on the left hand side is nothing but the derivative of p and t. So, we have dPnt to dt is equal to minus lambda times p and t. So, what happens to h here? So, if you see here, we have limit h tending to 0 is taken on this right hand side also. So, when you take the limit h tending to 0 here, it is O of h by h, but we have seen from the regularity postulate that limit h tending to 0 of O of h by h goes to 0. So, wherever this O of h by h is there, when you take the limit h tending to 0, that factor goes off, and hence we have this expression out here dpnt to dt equal to minus lambda pnt plus lambda times pn minus 1 of t, where n ranges from 1 to infinity. So, we write this is valid when n equal to 1, 2 and so on, but we need to write what happens when n equal to 0. So, that we will see after a short break. Welcome back after the break. We have to see this equation when n equal to 0. So, we need to derive this again separately. So, we consider P naught of t plus h, namely probability that n of t plus h is equal to 0. So, this is again the whole interval 0 to t plus h is divided into 0 to t and t to t plus h as before, and we have P naught of t, namely by time t there is no event, and in t to t plus h also there should not be any event. That probability is given by P naught of h, which is 1 minus lambda h plus order of h. So, as before we take limit h tending to 0 and take this P naught of t into 1 to the left hand side and divide both sides by h. So, the right hand side also has limit h tending to 0 here. So, limit h tending to 0 of P naught of t plus h minus P naught of t by h is equal to minus lambda h plus O of h by h into P naught of t, where limit h tending to 0. As before, we also have in this case on the right hand side O of h by h when limit h goes to 0 will be 0. So, we are left out with now dp naught t to dt is equal to minus lambda times P naught of t when n equal to 0. So, in this way now we have the system of equations dpnt to dt equal to minus lambda times pnt plus lambda times pn minus 1 of t, n equal to 1 to 3 and so on, and in the case when n equal to 0 we have dp naught t to dt equal to minus lambda times p naught of t. Now, we need to use these equations and get an expression for Pn of t, that is our goal. So, what we do here, because these are differential equations, we need the initial conditions to get the constant of integration and later on. So, n of 0 is 0. This is a sure event because ntt greater than or equal to 0 is a counting process. So, we have n of 0 equal to 0. So, which is a sure event, that is denoted by P naught of 0 is 1. Fine. Now, we will proceed with the next step, namely suppose the induction method, when n equal to 0 we consider this equation where we use the variable separable method. So, dp naught t by p naught t is given by minus lambda times dt. So, after integration on both sides we get log of p naught of t is equal to minus lambda times t plus c is the constant of integration. Now, use the initial condition to get c. So, put t equal to 0 on both sides, right hand side we get c and left hand side p naught of 0 which is 1. So, but log 1 we know that it is 0. So, finally, we get c equal to 0 and p naught of t equal to e power minus lambda t. So, in the expression for p and t, when you put p and t equal to e power minus lambda t per 0 by 0 factorial, you do get p naught of t is e power minus lambda t. So, in this way the result we have proved for n equal to 0. Next, we will consider n equal to 1. So, put n equal to 1 in the general equation what we saw earlier. So, dp1t to dt is equal to minus lambda times p1t plus lambda times p naught t. Having found the expression for p naught t as e power minus lambda t, plug in that expression out here, we have dp1t to dt equal to minus lambda times p1t plus lambda times e power minus lambda t. So, this further gives us the first order differential equation where we can use the complementary function, the integrating factor here. So, the integrating factor here would be lambda times integral dt. You remember dy by dx plus p times y equal to q, that is the equation type we are having it here. So, we use the integrating factor and write this solution out here. So, we have p1 of t into e power lambda t is equal to lambda times integral dt plus c. Once again we have the constant of integration c. As usual, we have to evaluate this constant by using the initial condition, because this is a differential equation. So, p1 of 0 is 0. Having used that, p naught of 0 is 1. For any other value of n, p n of 0 will be 0. So, once again we have p1 of 0 being 0, and here t is 0, we have c is 0. So, p1 of t we have into e power lambda t equal to lambda times t, which in turn gives us p1 of t is lambda t times e power minus lambda t. We have again proved the result for n equal to 1. Now, by the induction method, we assume the result to be true for n equal to k and prove it for n equal to k plus 1. So, in the following we consider the case when n equal to k plus 1. So, again we have this differential equation dp k plus 1 t to dt equal to minus lambda times p k plus 1 of t plus lambda times p k of t, that is minus lambda times p k plus 1 of t plus lambda times, we already have this expression, we are assuming the result to be true for n equal to k in terms of this p k of t. So, plug in that expression here and we have the following. So, once again you treat this as a first order differential equation of the form dy by dx plus py equal to q, use the integration factor and proceed to get the pk of t, so pk plus 1 of t. So, we are going to do that here, solving this pk plus 1 of t into e power lambda t is the integration factor. This is equal to, you take out the expression which has lambdas which are independent of t from the right hand side. So, we have lambda power k plus 1 by k factorial taken out, integral t power k e power minus lambda t, lambda into e power lambda t is integration factor dt plus c. So, once again we are having this e power lambda t into e power minus lambda t, which gives us 1, and we are left out with integral t power k dt. So, after integration this gives us t power k plus 1 by k plus 1, but this integration constant is there. So, as before, put t equal to 0 in pk plus 1 of t, but that is 0. So, once again right hand side is 0 here with c alone remaining. So, we have c is 0. Thus, plugging in c equal to 0 in this expression, we end up with pk plus 1 of t equal to e power minus lambda t into lambda t per k plus 1 by k plus 1 factorial. So, now we have proved the result for n equal to k plus 1. So, by the induction method we have established now that p n of t is e power minus lambda t power n by n factorial. Now, we will see the properties of Poisson process, which are also very important in queuing theory. The first property is the additive property. Suppose we are considering two Poisson processes which are independent, say with parameters lambda 1 and lambda 2 respectively. Then what is the distribution of n of t, say, which is nothing but n1 of t plus n2 of t. So, this n1 of t and n2 of t are two Poisson processes which are independent, each with the parameter lambda 1 and lambda 2 respectively. So, we have that probability of n of t equal to n is equal to e power minus lambda t power n by n factorial, where n equal to 0, 1, 2, 3 etc. But what is this capital lambda out here? That is nothing but, we will see shortly, it is lambda 1 plus lambda 2. So, the proof of this, we have to consider p of nt equal to n, but nt is n1t plus n2t. So, we write this as using the multiplication rule, namely P of the event A can be found as P of A given B into P of B. So, using this multiplication rule here, the event A is for you n1t plus n2t equal to n, but the event B is n1t equal to k. We know that two processes are here, we can use B as any of them, either n1t or n2t. So, here we are taking n1t to be equal to k, that is the number of events happening from the first process Poisson process n1t are k. So, P of n1 plus n2 equal to n. So, under the condition that n1t equal to k into P of n1t equal to k, but we know already that P of n1t equal to k is a Poisson distribution. So, with the parameter lambda 1, so we will be plugging in that there, and here we use the condition that n1t equal to k, put n1t equal to k, this becomes probability of n2t equal to n minus k given n1t equal to k into probability of n1t equal to k. But if you see here, we have in the conditioned part we have n1t and in the unconditioned part we have n2t. But what is the hypothesis here? N1t and N2t are both independent Poisson processes. So, we have something like here P of A given B, where A and B are independent. So, which means that P of A given B should be equal to P of A, and hence we have P of N2t equal to n minus k given n1t equal to k is nothing but P of N2t equal to n minus k. Now, we know that n1t is a Poisson process with parameter lambda 1, n2t is a Poisson process with parameter lambda 2. So, plug in the respective distributions as has been done here. Now, we know that this k is arbitrary, it is not fixed, and for each value of k you have that this event is a mutually exclusive event. So, we have to add up all those probabilities, that is why we have this sigma k equal to 0 to n being written here. So, this is to be simplified, and that is how it has been done here. We get e power minus lambda 1 plus lambda 2 into t power n sigma k equal to 0 to n. Those factors which have k dependency are being retained within the summation, rest have been taken out. Now, you can see that I want to write these as a binomial summation. So, I have to multiply and divide by n factorial here to be able to get or write this as nck. So, I am dividing here by n factorial, which is taken out, and the numerator n factorial is retained there, and this is nothing but represents a binomial series sum, which is lambda 1 plus lambda 2 power n. So, that is what has been written here, and hence we have this is equal to e power minus lambda 1 plus lambda 2 into t, lambda 1 plus lambda 2 into t whole power n by n factorial, which is nothing but the Poisson distribution. Hence, we have proved that the sum of two independent Poisson processes is a Poisson process with the parameter being the sum of the two individual parameters. So, the next property we will see is here, it is given as suppose we have a counting process nt and consider another time instant s less than t, which is given by that is the probability that n of s equal to k given nt equal to n. Here which time point is later, t is greater than s. So, given that under the knowledge that n events have already happened, what is the probability of k events happening in an interval which is prior to t? So, that probability is nothing but the binomial distribution. So, nck s by t power k into 1 minus s by t whole power n minus k, where k is from 0 to n. So, this is the example where we can link the Poisson process with the binomial distribution. So, we are not looking into the proofs of all this presently. So, we will see the next property, namely if n of t is a Poisson process, then the correlation coefficient between n of t and n of t plus s is given by square root of t by t plus s. So, you do know the definition of correlation coefficient, which is covariance of x comma y by sigma x into sigma y. So, you have to use this definition and prove this. Maybe you can take this as an exercise and the proofs of both these properties and see if you can solve them. So, maybe before concluding today's lecture, let us see if you can answer this two questions out here. I am giving you two questions based on Poisson process. So, the first one is problem is, suppose that you have events occurring, or it is earthquakes which occur in a certain region of California at a rate of 7 per year. So, earthquakes are happening at a rate of 7 per year according to a Poisson process. Two questions under this. What is the probability of no earthquake in 1 year? The second question is, what is the probability that in 3 of the next 8 years no earthquake occurs? So, there is a twist in the second subdivision. Just see if you can work out. The second question is, suppose that children are born at a Poisson rate of 5 per day in a certain hospital. What is the probability that at least 2 babies are born during the next 6 hours? The second subdivision is, what is the probability that no babies are born during the next 2 days? So, the clue is both are on Poisson process, the problems. So, just see if you can work out how much you have understood from today's lecture. So, we will meet in the next lecture. Thank you.